This will be the last section in chapter 16. This will be section 16.8. We're going to look at the Kelvin temperature scale, and we're going to see that it's based on the efficiency of the Carnot cycle, and that it's independent of the properties of any specific material. And also, the 0 point on the Kelvin scale is absolute zero. So what we're looking for when we studied temperature scales back in chapter 14, we expressed the need for a temperature scale that doesn't depend on the properties or behavior of any particular material. If we use the Carnot cycle to develop such a scale, we can accomplish this. So we know what the efficiency is of a Carnot engine operating between two heat reservoirs. We know how those ratios are equal to each other. If you look at this, it might look a lot like equation 16.7, but there's going to be a subtle and crucial difference. The temperatures in 16.7 are based on an ideal gas thermometer. But this defines a temperature scale that is based on the Carnot cycle and the second law of thermodynamics and is independent of the behavior of any particular substance. In that particular case, since it's independent of any particular substance, it is considered to be truly absolute. If we go further, we can assign an arbitrary value of 273.16 Kelvin to the temperature of the triple point of water. This is a unique temperature in which gas, liquid, and solid phases all coexist in phase equilibrium. When a substance is taken around the Carnot cycle, the ratio of the heat absorbed to the heat rejected is equal to the ratio of the temperatures of the reservoirs, as expressed on the gas scale. Since on both scales the triple point of water is chosen to be this temperature, it is found that the Kelvin and the ideal gas scales are considered to be identical. Also, the 0 point on the Kelvin scale is going to be absolute zero. There are theoretical reasons for believing that absolute zero cannot be obtained experimentally, although temperatures below 10 to the -7th Kelvin have been achieved. The more closely we approach it, the more difficult it is to get closer. Based on quantum effects, it would not be correct to say that at T is equal to zero, all molecular motion ceases. At absolute zero, the system has its minimum possible total energy. One statement of the third law of thermodynamics is that it's impossible to reach absolute zero in a finite number of thermodynamic steps.